Hello. In this video, I'm going to be solving exercise 0.3.101 from Jiří Lebel's Notes on Diffy Qs. These notes will be, or a link to them will be made available in the description. So in this problem, we're given a bunch of equations and we need to classify each of them. So for each, we need to determine if they are ODEs or PDEs, if we're given an equation or a system, the order of the equation slash system, whether the equation or system is linear or nonlinear, and if it is linear, is it homogeneous and of constant coefficients? And finally, if we're given an ODE, whether it's autonomous or not. So let's do these one by one, starting with problem A, part A. So already, the presence of these partial derivatives tells me that this has to be a PDE. So we can already jot this down for the first question. So here we're only given one equation. It would be a system if we had more than one equation, as in part E, but here we only have one equation, and so this is just an equation. What is the order of this equation? Well, we can see, the order by definition is the highest order derivative occurring in the equation. Now, the two derivatives that I see are both second order, so the highest order derivative, it has order 2, so this is second order. Now, we ask whether it's linear or nonlinear. Well, we can see that whenever we have a term involving a derivative or partial derivative of v or v itself. So here we just have the second partial derivatives of v. We're only multiplying them by things that possibly depend on the variables of v. So in this case, x and y. But in our case, these partial derivatives, we're actually only multiplying them by constant functions. So here we can think of there being an invisible 1. And for the next partial derivative, we're only multiplying by 3. And then on the right side, we just have all of the things that don't depend on our function v, nor any of its partial derivatives. And so this would be a linear equation. There's another way to determine whether an equation is linear or nonlinear, but that's something that I'll discuss in a later video. Right now, it's more pertinent to just recognize when a differential equation looks like a linear one or not. And for those of you that are curious, this, like what the general form of a linear equation is, have a look at page 18, equation 2 of the notes that I'm using. Okay, so this is a linear equation, and now this is linear, so now we need to ask if it is homogeneous or not. And here this equation is not, because all of the right side has something that depends only on the variables x and y. For this to be homogeneous, this right side would have to be 0, because then everything occurring on the left side of the equation would only depend on the function v or its partial derivatives, perhaps. So, but again, the right side is not 0, it's sine of x, so this is not homogeneous. Oh, I know a little caveat too. So if you look at equation 2 of the notes, you'll notice it's only phrased for an ODE. The way to kind of generalize this for a PDE, just if you're looking at the notes right now, is the right side should be a function depending on all of the variables of v, so here x and y, and then the left side will only occur with derivatives, partial derivatives of v, multiplied by functions that only depend on x and y. So if you're looking at the notes, those functions a0 up to an can only depend on x and y. Okay, so this is not homogeneous. And, well, it's not ODE, so we don't need to wonder whether it's autonomous or not. And so this completes the solution to part A. For part B, okay, so there are no partial derivatives occurring here, so this is an ODE. This is just a single equation, not a system. And what else? The order, well, here we only have a single derivative occurring, and it's a first order, so this is first order. Is it linear or nonlinear? Well, here, let's take a look at the terms one by one. Here we have a derivative, and we're not multiplying it by anything, but if you want, you can think of it being multiplied by the constant function 1. For the term x, we're multiplying it by something that doesn't depend on x. It only depends on the independent variable t. And so this counts for a linear equation. And on the right side, we have everything that doesn't depend on our function x. And so this would be a linear equation. And, well, now we know it's linear. Is it homogeneous? No, it is not. Well, for it to be homogeneous, note here that we would have to have the right side be all 0. But here we have t squared plus t plus 1, so this is not homogeneous. And is it autonomous? Well, an autonomous equation, recall, I'll write this in blue. Can be written in the form y prime equals f of y. And more generally, it's an equation that doesn't change with time, if that makes sense. So, like, let's say, for example, that we added a t here. Then this would no longer be autonomous because as t increases, the equation looks different. But if we erase the t, then as we increase t, the equation remains the same. So, looking up here, we can see that that's not the case because right here we have this cosine of t and this t squared plus t plus 1. And as we change t, the whole equation is going to change. And so this is not an autonomous equation. This is not autonomous. Let's do part C now. So here we have this equation. We have this derivative here, and it's of order 7. No other derivatives occurring, so the highest order is 7. And hopefully everyone agrees this is an ODE. There are no partial derivatives, so this is an ODE. Again, we have one equation, and the order is 7. Or let me write it like this. Is it linear? Well, looking at the form given here in this equation, it doesn't immediately fit that form, but we can make it fit that form if we rewrite it in a different way. So if we take this equation and we rewrite it as d7f over dx to the 7th minus 3f of x equals 0, then we do have it in the form that's given in this equation. And actually, to make everything self-contained, let me add that general form that they talk about. So a linear ODE specifically, looks like, and let me use Leibniz notation for this, plus a0y equals b, where the ai's, so from a0 up to an and b, are all functions of x. Only x. So looking here, we can see that this fits this form right here with b equal to 0, and then we only go up to 7, and then the coefficients are, well, -3, 0, 0, 0, 0, 0, all the way up to 1. So this is linear. It is also homogeneous because the right side, when we brought all of the terms involving f and stuff and its derivatives, when we brought all those to the left side, leaving all of the terms only depending on x on the right side, well, there were no terms. The right side was left to be 0, so this is homogeneous. And, oh, I just realized for part A, I forgot to say that the coefficient, this is a constant coefficient PDE because the coefficients in front of the derivatives. So note that this doesn't count as a coefficient because it's the right side of a linear differential equation. But everything else, all the coefficients are constant, so this is constant coefficient. And similarly for our part C, we can see here that all the coefficients are also constant, so this is also constant coefficient. Oh, and I just realized too, for part B, note here that one of our coefficients is cosine, which is not constant, so this is not constant coefficient. There we go. Now finally, we want to ask, whether this ODE here is autonomous. And it is autonomous here because we don't have any terms involving x. So like for example, if we had something like plus x squared plus x, this would no longer be autonomous because now we have a term right here that doesn't depend just on the function we're trying to solve for, f. And so, but again, our original ODE didn't have this property, so this is autonomous. Now let's do part D. So single derivatives, there's no partial derivatives, so this is an ODE. It's a single equation, so it's an equation. There we go. The order, well, we have a first derivative and we have a second derivative. The larger of the two derivatives is the second one. 2 is bigger than 1. So this is a second order ODE. And this is also linear because here we can see that our coefficients are 1, 8, and then the right side of our linear ODE is just the constant function 1. So this is a linear ODE. And moreover, it is also homogeneous and it is not homogeneous because this is 1 and not 0, but it is of constant coefficients because the coefficients, this invisible 1 and 8, are both constants. So let me write out everything we have so far. This is an ODE equation, second order. It is linear. It is not homogeneous. But it does have constant coefficients. And finally, is this autonomous? So it is. And the reason why is because this equation, again, using that intuition I gave earlier, this equation doesn't change over time. So notice how there are no terms here involving t, or if the independent variable was x, involving x. So as t evolves, this equation does not change at all. You still have, like at t equals 0, the equation is y double prime plus 8y prime plus equals 1. But if you go up to t equals 100, we still have the same equation. That would not be the case if we added, say, like plus t squared, because now the equation is changing over time. So this equation is autonomous. All right. So now this gets us to part E, and I'm going to add a page for this. So here we only have derivatives of functions of a single variable. That's what the primes denotes. So this is a ODE. And it's a system of ODEs, actually. And the order of this system is 2, because if we look at all the derivatives, we have a second derivative, first derivative, second derivative. And so the highest order derivative is 2. So this is ODE system. It is of second order. And this thing is not linear. The reason why is because here we notice that we are taking the two functions. So actually, let me rewind. So in the previous example here, like take this one, part B. Our independent variable was t, and the function we were solving for x was a function of t. Here, the functions we're solving for are x and y. We can tell because these are the functions that we're taking derivatives on. And presumably, the variable that they depend on is t. Since we are multiplying the two functions here together, and it's not unlike this case where x could be multiplied by something that only depends on its independent variable, the presence of these two terms here makes this a nonlinear equation. And so we can annotate this. This is nonlinear. And if it is an ODE, is it autonomous? Here, we don't, they don't define it in this book for a system, so we can't really answer whether this is autonomous or not. If you wanted to follow the intuition that I gave where like a ODE or system ODE of ODEs as autonomous doesn't change over time, then this wouldn't be autonomous. But that we don't define whether a system is autonomous or not autonomous in this book, so we leave that question unanswered. And finally, we're left with F. So hopefully everyone agrees this is a PDE. We have partial derivatives. This is a PDE. It's a single equation. And this PDE has order 2. We have a first derivative, second derivative. The biggest derivative has order 2, so this is second order. Is it linear or nonlinear? Well, here we just need to look at this u squared. This is a nonlinear function. When you square something, that's not linear. And so this fact alone that we have u, that we're squaring u, makes this whole equation nonlinear. And, well, now that we know it's nonlinear, we don't have to answer anything else. Okay, that wraps up this video. If there are any questions, please leave a comment. Otherwise, I'll see you all in the next video.